every one of the channels and did a basic two-sample t-test just to understand the significance. Got to narrow it down. I believe we ended up with, instead of the 137 some channels, we got narrowed down to 47 that were truly showing significant statistical significance there. Went back to our neural analysis and said, okay, let's try it with less variables this time to see what kind of model Jump's going to give us. Ran it, and we started getting a lot more believable type R values. The first one we looked at your R squared, very high, and then your validations were staying high. And we saw this consistently. It reruns a model every time, so you get different values. Sometimes they're not as high as that, but consistently we're hitting it right on. And the graphical will show the same thing. That it creates its model very concisely, and then it tests it, and it also validates pretty well its test. You want to show that graph? This is a good time to show that graphic of the diagram. So you saw that first. This one kind of still looks messy, but the first one was unbelievably messy. We were using 137 variables there. Very complex model we were sending to it, and it was getting a lot of variation based on that. We narrowed it down through that two-sample t-test to 47 channels, which made it a lot simpler model for Jump to understand. And therefore, we were consistently getting, you were saying, okay, you're giving me a simpler model. I'm going to give you some output just like I did before, but we're getting consistently better output transfer functions.
So the 47 channels are your X variables?
Yes.
Okay, so you basically reduced your X variables.
You simplified the model, yeah. Yeah, just claiming that the other ones were insignificant, whether you got a high score or not, we could use the average.
Ideally, I mean, the model shouldn't be able to select a variable that has significant correlation to your value. So if I throw in more variables, they should only pick those ones contributes more to the one, and then drop or give small weights to the ones that are maybe correlated to y function. So I couldn't comprehend why when you have less X variables, you could just change this story completely.
Well, I don't know a lot about neural networks, but one thing it does is these little called hidden nodes here, and the way I understand it is, or maybe the way I like to make it up is, it almost puts a random function in here. So it'll take one of these variables, do some random calculation and then compare it to the aggregate score. And it'll do it for all of them in a bunch of different ways. And that, because every time you run this, you get a different answer because it's constantly changing what these 5 things mean here. And so what we saw with the more variable, the more X varies, we saw a lot more variability. So sometimes we'd run a model, it'd be pretty good, and then when we tried to recreate it, it'd be terrible. And then we tried to run it again, and it wasn't 50, it was more like maybe a third or a fourth of the time at most. It was decent. Usually it was pretty bad. When we went to 5 nodes instead of 3 and we reduced this, we got a much more consistent, almost all our R-scores are almost always in the 90s. There was one in the 50s the first time I showed this, which is rare. But actually, these numbers are more typical, these are more typical of what we would see. These are actually high, a little higher than normal, but we would get in the 90s, high 80s.
Yeah, one thing we did, we'll share with you at the end, is we were talking with the folks at Jump throughout this journey and asking some of those questions. And the answer we got from this was the complexity we fed it at the beginning. Even though it is supposed to ideally filter out the ones that are insignificant, do kind of the work that we did manually, we were saying a very complex model, and when we simplified it, we got a little more consistent results, which we can see on this.
Well, also I should come up with is because all this neural network is a data mining system, and it's like a statistical method, whether you do regression or not. What it does is do the optimization in the background to estimate those parameters, the coefficients. So when you have too many X variables, and then they have to pick the transformation variables, and then this probably hiding nonlinear, so it could easily get stuck into local optimal. That's why every time you run it, you see different results,
Right.
because it gets stuck to local optimal. It depends on where you start, so you get different analysis.
Very good, thank you.
So we are feeling pretty comfortable about this. Every time we ran, like Rick mentioned, we're continually getting very, very good results. So we wanted to continue down this path. This is okay. I figured out a transfer function for you. Now what can you do with it? Going into a different platform that JMP has is this prediction profiler that Rick has up. So now that it has figured out a transfer function based on your data, JMP will allow you to change any one or multiple variables, which are the channels, and show you what the output would be. So for example, on L11, channel L11, Rick could select that value, and as he changes it through that spectrum, like if that EEG was reading these different values, how would that affect not only the other channels, but how would it affect the total score? Which becomes powerful because now we could use a prediction profiler to see if we could optimize our score, if you will. And this was exciting, but you know, we're still dealing with 47 different variables, so there's no way we could kind of manipulate it manually and try and figure it out. So we looked for other options that JMP, or other platforms that JMP had to offer, and they have another thing called Simulator that they say, okay, we'll do it for you. We'll run as many iterations as you want, and we'll spit out the output based on our transfer function, and then you pick whatever result you want, you have to see what the variables are. So what Rick's going to do is he put the number of runs there, very quick, but the number of runs can be set at whatever. We're doing 50,000 just for a large number that won't bog, because it bogs a microsecond on the computer, but 50,000 runs based on that transfer function. He selects run table, or make table, and there it spits it out. So you can see all the different variables, including the eyes open, closed, the discrete data that we use, and then at the end of the column it gives you the different scores that came about based on the transfer function. So what we did at this standpoint is we took the top 10%. We said, okay, we'd like your top 10% of your highest scores, average those, and and then I'll look to see what all the EEG readings were, and I want to recreate that helmet and see what that looks like. See if it looks like my smartest guy or gal that was on there. And that's what Rick's showing now. Is now that we had that, we recreated that 3D scatter plot, and this was the helmet that we got. And very interesting. We brought the client back at this time, and we said, you know, this is kind of interesting. It's got dots all over the place, and it looks nothing really like. We can't connect it with any one of the scores. And this was something that he was familiar with. He says, you know what? You guys are getting, I believe in your transfer function. You're getting a good computer representation of what the highest score would look like. And he said it's been a fault that the group has studied for a long time, is that a computer could come up with the perfect brain, but is it humanly possible? Maybe not. And that's kind of what we're seeing here. In no instance could we have this kind of disparity this close together as far as the difference in EEG readings and the proximity. We did, however, find some groups that were very similar to our high scorers that he was able to point out for us. So it was showing something that was confidence to him based on the data that he'd seen in his background. But it did also prove a point that a computer-generated transfer function may not represent what's humanly possible as far as creating a perfect model.
You couldn't have a brain that had all these different ranges of EEG readings. If you remember from the other ones, just back here, you know, all these, they might have 3 colors at the most, right? Kind of looking through. And our optimal brain's got like every color on it. So, but like David said.
It is. It's the actual. It grows as far as the score, the level of EEG reading. There wasn't a big difference, so you can sometimes pick them out, sometimes you can't, but it does.
It's an option, you can size them by value, you can program by value.
Right, so they'll size them correctly. So, yeah, all the red ones will be small, the orange ones are big, the higher EG areas will be small. Yeah.
So does it mean like when we're using our brain, we actually depends on the task we are doing, actually have those regions kind of highlighted. But it's rarely we have the whole brain all light up. That would be crazy, right? Because it depends on what task we are doing. We are thinking, we are writing, or we are reading in a different area of our brain or activated. That's what we saw in those.
In those first ones.
Yeah, the first one is like basically every point is activated, it's all active. So that's why
It's set up to be, what is optimal if you're going to try to maximize the aggregate test scores.
Yeah, like a fingerprint, if you will, of the brain. That's what it's kind of set up to be. But to your point, yeah, it's not realistic of what we think or what the patterns were for a brain. But if you went back to the sheet, so that kind of goes against our intuition. This is actual data. This is no transfer function. This doesn't really follow suit to what we would think if you did a certain activity, one side would light up. Everyone kind of reacts differently, so we're trying to just go off the data that we had to generate the transfer function based off of scores that actually happened. So with our analysis here,